Okay, the next thing we're going to look at is something called the scalar product. So the scalar product is the result of multiplying two vectors together, all right? So it's about multiplication of not a vector and a scalar. For example, 3 times the vector 1, 2, 3, that would be a vector multiplied by a scalar. This time what we're looking at is a vector multiplied by a vector. So for example, you might have a vector A and a vector B, and you're multiplying both of them together. So not a scalar multiplied by a vector, but a vector multiplied by a vector. Now, there's a formula that's given to you in the formula sheet, which is that the scalar product, now this dot in the middle is a symbol that can be used for multiplication. Maths is something that you wouldn't have seen before, but you're seeing it just now, and that denotes that we're multiplying together the vector A and the vector B. Now, there's a formula for that, which is the scalar product A dot B, the vector A times the vector B is equal to the magnitude of the vector A times the magnitude of the vector B times cos theta. This will be given to you in any formula sheet for an assessment. A dot B equals magnitude A times magnitude B times cos theta. Okay. Now, 2 points to note is that first point to take down is the vectors must point away from the vertex. Now, what that means is that when the vectors come together, okay, the vertex being the point at which they meet, which creates an angle theta, the vectors must point away from the vertex. Okay, so what you couldn't have is something like that, because what we've got there is one vector pointing away from the vertex and one pointing towards. It needs to be like this. Okay, that's point 1. Now, point 2 is the result is a scalar. What that means is when you find the scalar product, which is multiplying the two vectors together, what you get is a scalar result. So the product, the result of multiplication, is a scalar. Okay. So let's get straight in and try some examples then. Okay. So let's go for an example 1, and let's go for this one. Find A dot B given magnitude A equals 2, magnitude B equals 1, and theta equals pi over 6. Okay, so A dot B equals magnitude A times magnitude B times cos theta. A dot B equals, well, the magnitude of 1, as you can see, is 2 multiplied by the magnitude of B, which is 1, multiplied by cos theta, which is cos pi over 6. Now remember that pi over 6 is 30 degrees, so that's 2 times 1 is 2, multiplied by cos pi over 6, which is cos 30. Cos 30, we can pick up the exact values for that. Cos 30 is one of your 15 exact values that you should know, and that is root 3 over 2. I've now get 2 times root 3 over 2, the times 2 and divide 2 cancel out to give me a final answer of root 3. Okay, example 2, I'm going to supply a diagram with this one. So we're going to look for the scalar product A dot B, and we're going to say that the magnitude of A is 5 and the magnitude of B is 4. And this time, here's the diagram that's going to accompany the question. So in here we've got the angle, and the angle is 45 degrees. Okay, quick check. The vectors point away from the vertex, that's fine. So A dot B equals magnitude A times magnitude B times cos theta. Okay, magnitude A is 5 multiplied by magnitude B is 4 multiplied by cos theta, which is cos 45, okay, cos 45, that's another non-calculator question because that's one of my exact values, so that's 20 times 1 over root 2. Okay, and that is 20 over root 2. Now what we could do at that point is rationalize the denominator, which will give me 20 root 2 over root 2 times root 2 is 2, and then 20 over 2 is 10 root 2, and I would go ahead and definitely rationalise the denominator at that point because that is a good method for simplifying the result. So let's just go over it again. Magnitude 5, magnitude 4 multiplied by cos of theta, and theta is the angle 45. Quick check that the vectors are pointing away from the vertex. 20 times 1 over root 2, that's 20 over root 2. Top and bottom by root 2 gives me 20 root 2 over root 2 times root 2 is 2, and then these two can be simplified to give me a final answer of 10 root 2. Okay, in example 3, we're going to find a dot b given this information here. Okay, so I'm going to say that the magnitude of A is 6 and the magnitude of B is 7. There's a right angle in between. So A dot B equals magnitude A times magnitude B times cos theta. Okay, quick check. The vectors are pointing away from the vertex. Okay, so that's 6 times 7 times cos theta. The angle is 90 degrees. If you think then that's another one of your exact values, cos of 90. Well, cos of 90 is 0, so that means I've got 42 times 0, which is 0, A dot B equals 0. If you think now, no matter what size of the vectors we're here, if I'm going to multiply them with cos 90, I'm always going to multiply by 0, which gives me a generic result, which is that A dot B equals 0 when vectors are perpendicular. So let's put that down. That is a true result all the time. Perpendicular meaning what? Meaning that they create an angle of 90 degrees, because no matter what I multiply together by cos 90 will always give me 0, which means the full thing will always collapse to 0. Okay, so that's a result that's always true. A dot B equals 0 when vectors are perpendicular. Okay, let's try an example 4. Okay, example 4, let's this time go for this one. Okay, so we've got a vector P and a vector Q. I'm going to say that the vector P has got a magnitude of 10 and the vector Q has got a magnitude of 8. Okay, so P dot Q equals magnitude P times magnitude Q times cos theta. Okay, so that's 10 times 8 multiplied by cos theta, so cos of the angle is cos of 60. At that point, I'm just going to pause. Now, it'd be quite easy at this point to say 10 times 8 is 80 multiplied by cos 60, which is 1/2 of 80 to get a final answer of 40, which would be incorrect because it's quite nuanced. But what I really should do then is have a quick look at the diagram. Now, what I can see here is one of the vectors is pointing away from the vertex, as I'd hope, but one of them is pointing in. So that is not correct, okay, because it doesn't fulfill one of my expectations and one of my requirements, which is that the vectors must point away from the vertex. Okay, so what I've got is a bit of a problem to solve with this one. Now, this problem can be easily solved just by a wee bit of manipulation of the diagram. Okay, now remember one thing that I said from earlier on vectors, which is feel free to move vectors about. Okay, and if moving the vector is going to help us to solve the question, solve the problem within the question, that's something that we should look to do. Now, how about then if we took this vector here and we moved it down here, okay? So let's have this point fixed, but let's have this vector p moved down here. So if I'm going to move the vector p, it's just going to be a straight lift, and let's say I lift it from here down to here. Okay, it's still the vector p, okay? It's going in the same direction, it's the same size, I've just lifted it, and remember that I did say that vectors can be moved about, and we don't need to be fixed in a position with a vector, so we've moved it from there to there. Now, by doing so, what I've then did is manipulate the diagram so that vectors are now pointing away from the vertex, which creates this new angle here, okay? Now, this is now the angle that's appropriate to be calculating for these ones to be pointing away from this vertex, okay? So this time, what's this angle? Well, that's quite easy, because if we think about back to simple angle knowledge, that's a straight angle, 180 degrees. Now, if this bit here is 60, then I take that 60 off, leaves me with this bit, which must be 120 degrees. Okay, so now what I've got is 10 times 8 times cos 120. So that's 80 times cos 120. Now for cos 120, what I need to do next then is go to my cast diagram and start to pick up some of my acquired trig knowledge. Okay, so 120 lies in the sine quadrant, causes negative in the sine quadrant, and my acute angle then is going to be 60 degrees. So cos of 60 is 1/2, so that is minus 1/2. So that is now 80 multiplied by minus 1/2, and that gives me a final answer of minus 40. And let me just go over this question again and give a summary. Okay, first problem was it was easy to fall into the trap of putting down cos 60 because that's the angle I see. However, that angle is pointing away from the vertex, but this one's not, it's pointing in. I need to find angles to point away from the vertex. So what I'm doing then is moving this vector down here, which creates a new angle with vectors now pointing away from the vertex, given this angle here. Okay, now what that does then is it creates a straight line. If this bit, the straight angle is 60 degrees, this bit here must be 120 degrees, so that's my new angle that's created in between the vectors pointing away from each other from this vertex. Okay, the angle is 120, so it's then 10 times 8 times cos 120. Establish my exact value from up here in my trig knowledge to get minus 40. Okay, example 5. Let's go for this one. Okay, I've got vector A and a vector B, and the angle in between is pi over 6. Okay, the magnitude of vector A is 7, the magnitude of vector B is 4. Okay, so A dot B equals magnitude A times magnitude B times cos theta, and the vectors must point away from the vertex. So I've got a position and a problem here, which is that this one does point away from the vertex, this one points in. So again, it's about moving this vector over this time. So we're going to move this vector over here, which is going to create a new angle. So vectors are now pointing away from the vertex, but creating a new angle. Okay, so remember that the straight angle is 180 degrees. Now what's 180 degrees in radians? 180 degrees in radians is pi radians, okay? Because remember that pi equals 180 degrees. Okay, so think about what size this angle in here will be then. So if I take off the pi over 6 from the pi radians, well, if you think about a pizza and you take away 1/6 of a pizza, that leaves you with 5 pi over 6. So this angle in here then is 5 pi over 6. So that's 7 times 4 times cos 5 pi over 6. 7 times 4 is 28. What about cos 5 pi over 6? So I think we need to go to the side again and work that one out. Okay, so pi over 6 is 30. Times that by 5 is 150. Cos 150. Let's establish what cos 150 is. Okay, so I'm in the sine quadrant. Cos is negative in the sine quadrant. And my acute angle here is going to be 30 degrees. Okay, cos of 30 is root 3 over 2, so that's minus root 3 over 2. Okay, so it's minus 28 root 3 over 2. These cancel out to give me a final answer then, which would be minus 14 root 3. Okay, next we're going to try these ones. We're looking at operating with these unit vectors here. The magnitude of I is equal to 1, the magnitude of j is equal to 1, and the magnitude of k is equal to 1. We've seen these before. How do I know that they're all equal to 1? Well, they're unit vectors, okay, and unitary meaning 1. And remember that I is the vector, the unit vector, magnitude of 1 that points in the x direction, j, same bit in the y direction, k, same bit in the k direction. And remember that I and j are at a right angle to each other, as is j and k, as is I and k. So these all operate at right angles towards each other. Okay. Now, what about I dot k? Well, I dot k then would be magnitude I times magnitude k times cos theta. Well, the magnitude of I, it's a unit vector, is 1. Magnitude of k, well, that's a unit vector, is 1 again, multiplied by cos theta. And the angle in between the z-axis and the x-axis is 90 degrees, so that's cos of 90. Okay, so cos of 90 is 0, so the full thing collapses down to 0. I dot k is equal to 0. What about j dot j? Well, magnitude j times magnitude j times cos theta. Okay, so that is 1 times cos theta. Okay, what's the angle in between j and j? Well, they lie on top of each other, which means there's no angle. That's cos of 0. Cos of 0 then is equal to 1. So that means that j dot j would be equal to 1. Okay, next thing we're going to look at is the component form of the scalar product. Now, this is a scenario in which you're not necessarily given the diagram and the magnitude of the vectors with the angle in between. Instead, you're presented with column vectors. So let's say you're given the column vector, which is A1, A2, A3, and then another column vector, which is B, which we're going to say is get the components B1, B2, B3. Okay. This time, if you're given the component form, the scalar product is given by A1, B1, so that's A1 times B1, plus A2 times B2, plus A3 times B3, and that is called the component form of the scalar product. It will also be given to you in your formula sheet. It's dead easy, we're going to use it just now. So, we're going to find A dot B given. Okay, question A. Magnitude A, or rather vector A I should say, is 1, 3, minus 4. And vector B is 2, 6, 2. Okay, so A dot B then is equal to A1, B1 plus A2, B2 plus A3, B3. Okay, so that is 1 times 2 plus 3 times 6 plus minus 4 times 2. That's 2 plus 18 minus 8. And that'll give me 12. Okay, this one we're looking for P dot Q dot P dot R. Okay, so P dot Q dot P dot R is equal to the magnitude of PQ multiplied by the magnitude of PR multiplied by cos of the angle in between, which is QPR. Okay, so the magnitude of PQ, well, that's a position vector, so we'll need to do Q minus P. So that's going to be 5 minus 3, 0, minus 1, 2, 3. Okay, 5 minus 1 is 4, minus 3 minus 2 is minus 5, and 0 minus 3 is minus 3. Okay, I've then got PR, which is R minus P, and that is minus 1, 0, 4, minus 1, 2, 3, minus 1 is minus 2, 0 minus 2 is minus 2, and 4 minus 3 is 1. Okay, right, so one point to note is I'm not given information about the angle, so I can't use this method. I'll need to use component form, but that's dead easy. So that's just going to be PQ dot PR equals 4 times minus 2. So this is just the A1B1 plus A2B2 plus A3B3 method. So 4 times minus 2 is minus 8 plus minus 5 times minus 2 plus minus 3 times 1. Okay, so let's just go over that again. So 4 times minus 2 plus minus 5 times minus 2 plus minus 3 times 1. So that's minus 8 plus 10 minus 3, and that will give me minus 1.